Alright, in this video we are going to find or calculate the null space of a matrix. So we're going to be doing this in the next couple of videos, and we've done this before for a 2x3 matrix, so let's do it now for another rectangular matrix. This time the matrix is 4x3. So how do we find the null space? Well, we know that the null space of A is defined as the set of solutions, or the set of vectors x, such that ax equals the 0 vector. And we proved in the last video that this does form a subspace. So the set of all solutions x to ax equals 0. So to find the null space of a matrix, essentially what we need to do is solve this matrix equation. And the way that we do that is with the familiar method of row operations. So before we get started with that, let's see if we can come up with a list of expectations. So let's make a list of intuition / expectations. So first, if we just give this matrix a cursory glance, one thing that you might notice is that column 1 plus column 2 gives us column 3. So what we're expecting here, the columns are dependent. And so what we're going to expect is that, well, there's a total, I guess number 2 is that there's a max of 3 pivots. And because the columns are dependent, what we're going to be expecting from this is that there are going to be less than 3 pivots. Specifically, we might expect that there are going to be 2, because if we remove column 3 from consideration here, we see that these two vectors, column 1 and column 2, are certainly independent. So we're going to guess, of course elimination will show this to us, we're going to guess that there are 2 pivot columns and 1 free column. So you can't always do this, of course. This matrix actually was carefully constructed so that we could, but it's nice to know what to expect if just a cursory glance can give us valuable information like this. So we have a little bit of an idea of what to expect. Okay, so our goal is going to be to solve ax equals 0 using row operations. So we want to use row operations to take this into echelon form. So echelon form is essentially what we call the version of upper triangular form for non-square matrices. So we're going to use some row operations, which we'll do later, to transform this into echelon form. So before we get started, let's actually review what this means. In the previous video, I said that echelon form was the form in which we have zeros to the left of and below all pivots. And I could have been a little bit clearer on that, because I realized that there are some points of, potentially some points of confusion. So we do want zeros below and left of all pivots. But, for example, if we have, say, this 1 right here is going to turn out to be a pivot position. The 1, 1 entry in this matrix is going to be a pivot end. Well, there's no potential for zeros to the left of it. Also, if we end up, it won't happen with this matrix, of course, but if we end up with a pivot in the bottom rightmost entry as well, well, then there won't be any zeros. There won't be any zeros beneath it, assuming that we've row exchanged out of any rows of zeros. So let me add in, and I realize that this isn't as precise as it could be, but let's say when possible. All right, and also, one other point of clarification, echelon form also includes all rows of zeros at the bottom. So another very descriptive term that I've heard for echelon form is staircase form, and that the pivots create a staircase as we move through the matrix. So this is a review of echelon form. This is what we want to transform this matrix A into. But let's talk for a brief second about why this works. So we're not just concerned with finding the answers, we also want to understand what's going on behind the scenes. So the question is, so we're making an assumption here. The assumption that we're making, let's ask, so why is the null space of A equal to the null space of the echelon form of A? So that's the question, that's the assumption that we're making. And the answer is because row operations preserve solutions to systems of linear equations. So row operations preserve solutions. This is the foundation of the process of elimination. Indeed, if this was not true, then we would not use row operations to solve systems of linear equations. And as we can see up here, the null space of a matrix is certainly a set of solutions. So in other words, row operations may change the matrix, but it does not change the set of all x because the row operations themselves preserve the solutions. So we've done a lot of talking about what our goals are, what our expectations are, and the rationale behind those methods. So let's actually get down to the process of elimination. Alright, so let's do some row operations here. So let me rewrite our matrix. Now remember, when you're solving a matrix equation where the right hand side is nothing but zeros, there's no need to use an augmented matrix because, well, any linear combination of those zeros is just going to be 0. So you can just save some space and a little bit of time and just leave it out. Whoops. Two, 4, 5, and 6. There we go. Alright, so we have our first pivot right here. So essentially our first goal in elimination is to make all of these zeros to get it into echelon form. So we want zeros below all of the pivots, and so we want to eliminate 3, 4, and 5 and turn them into zeros with row operations. So I of course have some notes here because it's dangerous to do row operations, to record yourself doing row operations without having done them first because of the potential for silly arithmetic errors. But you should take the time, and I'll explain them, but you should take the time to verify and make sure that they're right for yourself, and also that you understand why we're doing the row operations that we're doing. So the first one here, it's always nice when we have a pivot of a first pivot of 1 because that makes the row operations somewhat easy, and we'll return to that idea of how nice it is that the pivots are 1 in perhaps a future video. So let's take 3 times row 1 and subtract that from row 2 and put the result in row 2. So what that's going to give us is a matrix in which rows 1, 3, and 4 stay the same because we haven't done anything to those rows, and row 2 becomes, let's see, 3 times 1 minus 3 gives us 0, and we do this process all the way across. 1 times 3 minus 1 gives us 2, and it gives us 2 in the next entry as well. Okay, this is good because we've eliminated the entry right below the pivot, so our next target is this 4. So again, the 1 in the pivot position is very handy. We can take 4 times row 1, subtract row 3, and put the result in row 3, and this is going to give us, now I'm going to write rows 1, 2, and 4 behind the scenes here. So there we go, rows 1, 2, and 4 stay exactly the same, and I'll change colors to write in the new one. Maybe I'll start doing that. So in row 3, if we perform this row operation, we get a 0 as expected, and then 2 3s. So you can see some similarity here. You can indeed see that these two rows are scalar multiples of each other. For example, row 2 times 3/2 would get us to row 3, or row 3 times 2/3 would get us to row 2. But perhaps it would be even more obvious, so you could take care of it with some kind of fractional multiple. To make it just glaringly obvious, since we're in a video and we have the time here, let's scale them both. So row 2 by 1/2 and row 3 by 1/3. So we're changing 2 rows here. Typically, I only like to do one at a time, but these are so simple that that it's worth doing. There's not much potential for a mistake here. So let's write out the rows that don't change first. There we go, magically appearing out of nowhere, and our new rows. You can see now, if it wasn't clear before, why we wanted to make this clear by multiplying R1 and R2 by a scalar, is that now it's very, very obvious that they were linear or scalar multiples of each other. So we can, well, instead of going straight ahead to the 5, it's pretty clear right now that what we can do is subtract R2 from, or R3 from R2 rather, and just eliminate R2 all, or how about let's put that in R3. There we go. Put that in R3 and eliminate R3 altogether. So let's rewrite the rows that are the same. There we have it. And now let's fill in the new row, which as expected is going to be a row of zeros. Now remember, echelon form up here says that the row of zeros have to be at the bottom. So the next thing that we're going to do is a row exchange. And exchange R3 with R4 so that we get our row of zeros at the very bottom. So R3 and R4, let's see if I can fit it in right on the edge here. So nothing happens with rows 1 and 2, and we switch rows 3 and 4. Now our target is this 5, so we push 5 to the side back here when we were at this stage so that we could eliminate an entire row. We couldn't pass that up. And so now we want to eliminate this 5, which is moved up into row 3. So we're going to take care of this just like we took care of all of the other entries. And let's see, we can take 5 times row 1 and subtract it from row 3 and put the result in R3. So let's rewrite the rows that stay the same. And 5 times row 1 minus row 3 is going to give us a 0 in the 3, 1 position. Okay, 5 times this entry minus this entry, so 5 times 1 minus 1 is going to give us a 4, and then 2 times 5 minus 6 is going to give us another 4. So here we can see pretty clearly from this that we can eliminate another entire row. We have 0, 4, 4 is obviously a scalar multiple of 0, 1, 1. And this time, because it's a little bit clearer, we don't have to involve fractional multiples. Instead of scaling this down to 0, 1, 1, what we can just do is say, well, 4 times, whoops, not row 1, 4 times row 2 minus row 3. If we put that in R3, that will give us a row of zeros. So there are the rows that stay the same, and we get our row of zeros. So this appears to be in echelon form. Let's double check. We have zeros below all of the pivots when possible and to the left of all pivots when possible, and we have all of our rows of 0 at the bottom. So this is the matrix U, and it is in echelon form. And since we know that the null space of this matrix is the same as the null space of this matrix, we are going to proceed and write the corresponding system of equations that can help us find the null space of this matrix here. So let's give ourselves some room to do that. All right, let's write down the system of equations that this corresponds to. So we have x1. Actually, before we do that, let's mark the pivot columns and the free columns and see if that agrees with our expectations, the intuition that we had at the very beginning. So these are the pivot columns. Okay, these are the pivot columns, meaning that x1 and x2 are what we call pivot variables. And x3, or the third column here, this is a free column. And you might remember from the previous video, we call it free because none of the steps that we took in elimination, for the most part, were aimed at anything happening in the third column. So our elimination process, how we selected our row operations, was more or less independent, completely independent of column 3. And what this means is that we can generate solutions to the matrix equation just by picking values for x3 and plugging them in, and as we'll see, that's what we'll do here. So the system of equations that corresponds to our echelon form is x1 plus x2 plus x3, and don't forget our right hand side was and will always be, in this case, 0, and then we have x2 plus x3 equals 0. So what this means, the fact that rows 3 and 4 equaled 0, elimination found that that these two rows were linear combinations of the previous rows. So this is elimination's way of telling us that, well, these rows have nothing additional to contribute. All the information that we need is contained in rows 1 and 2. Now, remember, we did some row exchanges at some point, so it doesn't correspond to row 3 and row 4 of the original matrix. So really what we can take from this is that 2 rows could be written as linear combinations of the previous rows. Now, we said that x3 was a free column. So let's focus on x3, which means that we can pick anything that we want for x3 and plug it in and generate a solution in the null space. So why not start with the most simple thing to plug in, which is x3 equals 0. So if we plug in x3 equals 0, we can see that, well, if we plug it in right here into the second equation, we get x2 equals 0. And so now if we have x2 and x3 equals 0, we have x1 plus 0 plus 0 equals 0. So we get actually that all of the components are equal to 0, which unfortunately this tells us that the vector 0, 0, 0 is in the null space, which does not tell us anything because we already knew that the null space was a subspace, and by necessity the 0 vector is in every vector space, is in every subspace. So this makes us, well, sad, or at the very least it's, well, it means that we have to do a little bit more work. This gives us no new information. So another easy value that we can plug in, another convenient value to plug in that is sure not to produce the 0 vector, is x3 equal to 1. So let's see about this. If we plug in x3 equal to 1 up here, then we get that x2 plus 1 equals 0. So this gives us that x2 equals minus 1. And if we plug this information into the top equation, so we essentially what we're doing is we're picking values for x3 and then proceeding by back substitution, just like we did for square matrices, for square systems of linear equations. So if we plug in a 1 for x3, that gives us x2 equals minus 1. And if x2 is equal to minus 1, then this gives us that x1 is equal to minus 1 as well, if we solve that equation, which gives us the vector minus 1, minus 1, 1, x1, x2, and x3. And this gives us information that we didn't know before, and we like this. So the next question is, what are some other vectors in the null space? So this vector right here, let me get the smiley face out of the way. This is a vector in the null space. So now the question is, how do we find other solutions, or how do we find other elements of the null space? maybe a better word here is generate. How do we generate other elements of n of a? Well, one method that we could use is we could plug in an arbitrary constant here. So we could plug in a constant k or something of that nature and work through it. And so what you would find is that this would, if we plugged in, say if we plugged in k right here, well, if you went back through and solved this, this would give you x2 equals minus k and x1 equals minus k as well. So what we can take this to mean is that, well, okay, well, the vector minus k, and k is also in the null space. So what we can say from that is, well, the null space then is the set of all scalar multiples of the vector, of our original vector. So minus 1, 1, and there's nothing specific about k other than the fact that it was a real valued scalar. So this is our complete null space, the set of scalar multiples of this vector fill the entire null space. And geometrically this is a line through the origin. The span, so this is the span of this vector, it forms a line through the origin. Now, we could have figured this out without actually plugging in an arbitrary value, so this was more to illustrate the greater point. So we know that n of a is a subspace, and there's value in that. So we automatically, if we had made use of our knowledge of subspaces, since n of a is a subspace, we automatically knew that all linear combinations of this vector, so the original vector, minus 1, 1, we automatically knew that all scalar multiples, all linear combinations of this vector were in the null space. So this is the rationale that we're going to adopt, and the rationale that we're going to use in subsequent examples to calculate the null space is that we know that it's closed under linear combinations, and so we're going to make use of that fact. And so typically what we're going to do is we're going to plug in ones for the free variables and then make use of the fact that we know that it's closed under an arbitrary scaling and an arbitrary vector addition, so more generally that it's closed under all linear combinations. So our main objective is completed, but there's an important question that I want to ask here. So this entire method was based on the fact that the null space of the echelon form of a matrix was equal to the null space of the additional matrix. So the other subspace, the other very important subspace that we know is the column space. So let's see, how can we write this? So the null space is preserved by row operations. So null space is reserved by row ops, and the symbolic way that we can write this is n of a, the null space of a equals the null space of u. And this is because the null space is a set of solutions, and we know from the very beginning of the class that row operations preserve solutions to systems of linear equations. The entire process of elimination is based on that fact. So the null space is safe. My question is this true for the other important subspace related to this matrix equation? Is the same true for the column space? So is this true for the column space? So what I'm going to do quite quickly is write down our original matrix A and then our reduced matrix, because we have a nice example that we've already worked through. Let's use it to our advantage and use it to answer this question. Alright, so there are the two matrices that we've been working with in this problem, and we had row operations to take us between the two. And, oh, I forgot to do this earlier. So I used the metaphor of a staircase and then never illustrated it. So you can see here that if you take the pivots and make a staircase with them, or it makes a staircase form. Okay, so despite my terrible explanation there. So now the question is, are the column spaces of these two matrices equal? So that's an equivalent way of answering this question. Is the column space of A equal to the column space of U? So let's take, I don't know, a vector that's very clearly in the column space, one of the columns. So how about 1, 1, 1? And start by asking, is 1, 1, 1 in the column space of U? Because if they're equal, this should certainly be true. And remember, the column space of U is the set of all possible linear combinations, or the span of its columns. So we have 1, 0, 0, 0. I'm going to run out of room here, I'm afraid. 1, 0, 0, 0, 1, 1, 0, 0, and I'm going to bleed over into the next line. 2, 1, 0, 0. So the one thing, got a little carried away with my curvy brackets there. So is 1, 1, 1, 1 in the column space of U? The answer is pretty, I think we can see here that any vector that's going to be in this span, well, any vector that's in this span is going to have a 0 for its last two components. If you look at all of these generating vectors for the column space, they all have zeros in their third and fourth components, and that is certainly not the case right here. So no linear combination is going to fix that. So alternatively stated, any linear combination of these three vectors is also going to have zeros in its final three components. And if you need some convincing, I urge you just to take some linear combinations of this. So 3 times this vector minus 2 times this vector plus 5 times this vector, for example. I don't know what that is off the top of my head, but I do know that the last two components will always be 0. So the answer to this question is no, and this is also the same answer to this question. Is this true for the column space? No. So this is pretty conclusive. This is a counterexample. So row operations do not preserve the column space. This will be very important down the line, and this example was a very convenient way of answering this question. So this will come up again. Row operations do not preserve the column space. So let's, this has been a somewhat lengthy video. Let's review the key points. I'll leave that last little bit that we did up there, actually. So let's review the key points. So I'm going to write out a list of summary points really quick. There we go, that was fast. So we went through a process or algorithm to calculate the null space of a matrix. So we started by solving AX equals 0. The first step was to reduce it to echelon form using row operations. Once we had it in echelon form, we did back substitution with the free variable equal to 1. Remember, the free variable equal to 0 did not really help all that much. And in fact, it provided no additional information. So plugging in this 1 is going to be key, especially in future videos. And then 3, we invoked the properties of subspaces. In other words, the defining characteristic of a subspace is that it's closed under linear combinations, and specifically in this case, we made use of scalar multiples. So the second key important point that this hinges on is that row operations preserve the null space. So that's going to be the next part of the summary. There we go. So the null space of the original matrix is the null space of the echelon form of the matrix. But the follow-up to that, you will recall, is that so row operations preserve the null space, and this is more of a continuation, but not the column space. So this is a very important fact to remember. Oop. There we go. Column space of A does not necessarily boy, I just want to seem to write ins, does not equal the column space of U and in general. In general, and the example that we had in this problem up here provides nice evidence of that fact. Let's give ourselves, so there's one or two other remarks that I want to conclude with. And one of them is in regards to the number of pivots. So we had an idea about this with some intuition right from the very beginning. So the number of pivots, or the number of pivot columns or variables, however you want to think of it, we call this the rank of the matrix A. So this is going to be used synonymously. When we say the rank of the matrix A, we just mean the number of pivots, and sometimes it's referred to, we just write, well, rank of A. Sometimes we'll just use R or R of A or some combination thereof. This is also equal to the total number of, or the maximum number of independent columns. So this is more foreshadowing of important ideas to come, but it's very, very related to what we did, so I'll include it in the summary. This is more of a looking forward remark. So the number of independent columns. Okay, so we came up with a processor algorithm to calculate the null space. We found out that row operations preserve the null space, or we didn't find that out, we more used previous knowledge to explain that fact, and then we verified that it does not preserve the column space, and the number of pivots, this is going to be very important going forward, and just like the number of pivots will be integral, so will the number of free columns, and we'll see that in the next video.